Okay, let's unpack this. Lithium, the unsung hero of our modern tech, is more in demand than ever.
Absolutely. It's that white gold, right?
Mm.
Powering EVs, phones, grid storage, everything.
Exactly. It's critical for, our sustainable future.
Hmm.
And the projections are just staggering.
Doubling by 2030, they say.
More than double, and nearly quadruple by 2040. So the big question isn't just if we need more lithium.
It's where does it come from? And crucially, how do we get it sustainably,
Yeah.
efficiently?
Yeah, to meet this huge global appetite.
And, if you look at the bigger picture, the urgency isn't just about the demand. It's finding smarter, greener ways.
Greener, definitely.
Because historically, a lot came from hard rock mining, which is, well, it's tough on the environment.
Right. Very resource intensive.
Yeah.
And geographically limited, too, which brings its own problems.
Precisely. Ecological and geopolitical challenges. So this idea of direct lithium extraction, DLE, from brines.
Brines. So like super salty water.
Yeah, exactly. Think huge salt lakes or even wastewater from geothermal plants. It's a really promising alternative.
Okay.
It could unlock vast lithium reserves, maybe make access more democratic, and hopefully have a much smaller environmental footprint.
But it's not straightforward, you said.
Far from simple.
Yeah.
The real headache is separating the lithium ions, the Li+, from everything else in that liquid, especially the unwanted stuff that's way more common.
And that's where today's deep dive gets really interesting, isn't it? We're looking at a potential solution, these novel polymer membranes, tiny, tiny pores, sub-nanometer scale.
Engineered right down at the molecular level.
Yeah, designed specifically for this separation challenge. So today we're diving into what could be maybe a shortcut to a more sustainable lithium supply for all of us from sources we might have just ignored before.
It's fascinating stuff. And the difficulty, it really comes down to a microscopic balancing act. It's stumped people for decades.
Because the brine isn't just lithium and water.
Oh no, it's a real chemical cocktail. Loads of different positively charged ions swimming around.
And the main troublemaker is?
Often magnesium. Mg2+ log.
Yeah.
It's frequently there in much, much higher concentrations than the lithium.
How much higher are we talking?
Well, in some salt lakes, the magnesium to lithium ratio can be like 60 to 1.
60? Wow, okay, that's a challenge.
It's monumental.
Yeah.
And they're both positively charged, so you can't just zap them apart with electricity easily. You need something way more precise.
Right, and that really highlights the core problem, doesn't it? Even down at that tiny scale, lithium and magnesium look surprisingly similar once they're dissolved.
Exactly. It's about their hydrated diameter. When an ion hits water, it gets this little cloak of water molecules.
Its hydration shell.
Yeah, and that's the size the membrane sees. Lithium ion, Li plus smoke, it's about 7.64 angstroms across with its water cloak.
Okay.
Magnesium, Mg2+ smoke, is just a tiny bit bigger, 8.56 angstroms.
Less than 1 angstrom difference.
Seems tiny to us, but at the nanoscale, it's huge. That's why older methods struggle.
It's like that analogy, trying to sift fine sand from slightly less fine sand with a regular kitchen colander.
Perfect analogy. It's practically impossible. Everything just goes through.
So conventional membranes, with their kind of messy, disordered pores, they just can't tell the difference well enough.
Exactly. They have what's called pore ion selectivity, often below 10 for Li plus Mg2 plus Li away, just lets way too much magnesium sneak through.
So even that tiny size difference is a massive barrier for the older tech.
It really is. And what's fascinating is why those conventional membranes fail. Often, the polymer chains they're made of can move around too much.
They're not rigid enough.
Right. There's high chain mobility, phase separations. Basically, it creates these large, inconsistent channels. No precision. They just aren't good molecular bouncers.
Okay.
Now, there are other advanced materials out there, things like MOFs, COFs, even graphene sheets.
Metal organic frameworks, covalent organic frameworks.
Yeah, they can be incredibly selective, theoretically.
Yeah.
But the problem is often manufacturing.
Hard to scale up.
Exactly. Expensive, difficult to make into large, stable sheets you can actually use in an industrial setting. Just not practical for the sheer volume of brine you need to process.
So for years, scientists were stuck trying this, trying that, hurdle after hurdle, until
this new class of materials came along. Polymers of intrinsic microporosity.
PIMs.
PIMs. Okay, what makes them special?
They're not your average polymer. Their structure is really unique. The backbones are incredibly rigid and, contorted, twisted.
So they can't pack together neatly?
Exactly. They physically can't pack efficiently. And because of that, they automatically form these permanent interconnected tiny channels all through the material. Like an internal network of pores.
Hourglass-shaped size-selective channels, the paper says.
That's the one. And here's the kicker for industry. PIMs are solution-processable,
Meaning,
meaning you can dissolve the polymer, cast it, like painting it onto a surface, and it solidifies into your membrane film.
so you can make big sheets easily. Precisely. Like the 25 by 27 centimeter one they made in the study.
Okay.
You can potentially use existing industrial roll-to-roll coating lines.
Wow, okay. That's huge. That makes it viable for actual factories, not just labs.
It's a massive advantage. It bridges that gap from lab curiosity
Yeah.
to something you can actually scale up.
But it wasn't just any PIM they used here, right? There was another innovation.
Correct. The core innovation was adding specific hydrophilic functional groups into these PM structures.
Hydrophilic meaning water-loving.
Exactly. Groups like amidoxime, carboxylic acid, hydroxyl groups, they do two crucial things.
Okay.
One, they track water, which keeps the channels wet and open for ions, essential. Two, and this is really key, they form these rigid networks through hydrogen bonding.
Within the polymer chains and between them.
Yes, it kind of locks the structure in place, makes it even more rigid, and critically, it helps create and maintain those incredibly narrow sub-nanometer size ion channels.
Tightening up those molecular bouncers at the door.
You got it. Making sure only the right size gets through consistently.
Okay, so it sounds like these membranes aren't just using one trick. It's more like a combination of things working together.
Definitely. It's a synergistic effect. Multiple mechanisms working in concert to achieve that selectivity.
So the first one is just pure physical blocking, what they call size sieving.
That's the most intuitive one.
Yeah.
The narrow channels, especially the bottlenecks, the dynamic pore gates, simply block larger ions physically.
Like a bouncer checking IDs? Or sizes, I guess?
Kind of, yeah. And these gates aren't perfectly rigid holes. They have a little bit of dynamic flexibility. The AOPN1 membrane, for instance, has an average gate size around 4 angstroms, plus or minus a bit.
Just right for lithium. Too small for magnesium with its water cloak.
Pretty much. It physically restricts the bigger guy.
Okay, but that's not the whole story.
No. Beyond just fitting through, there's an energy cost. That's the regulated dehydration part.
Dehydration, taking off the water cloak.
Exactly. To squeeze through those tiny pores, ions have to shed some of their water molecules. Think of taking off a bulky coat to get through a narrow door.
Makes sense.
Now, ions with a higher charge, like Mg2 plus S, they hold on to their water molecules much more tightly because of their stronger electric field. They're clingier.
So it takes more energy for magnesium to shed water than for lithium.
A lot more energy.
Wow.
That creates a higher energy barrier for magnesium to actually move through the membrane. Simulations show this really nicely in the 90s that lithium can partially dehydrate relatively easily, but magnesium holds on to more water, making it sluggish.
Interesting. Okay, size sieving, dehydration energy.
Well,
What else?
then you've got the chemistry inside the pore itself, electrostatic interactions, and ion binding.
So how the ions interact with the membrane walls.
Precisely. Those hydrophilic groups, especially the amidoxime ones, they're designed to interact preferentially with the single-charged alkali ions, Li plus Rn, Na plus Rk plus R.
So they like lithium more than magnesium.
Well, it's a bit more nuanced. There's actually quite strong binding between the hydroxyl groups in the amidoxime and the ions, especially with divalent ions like Mg2 plus S.
Yet strong binding with magnesium. Wouldn't that trap it?
Sort of. It creates a high energy barrier for diffusion. It's like magnesium gets momentarily stuck, interacting with the pore walls much more strongly than lithium does. Lithium can interact favorably but still move along. Magnesium gets slowed right down.
Okay, I see. It hinders magnesium's movement through the channel.
Exactly.
Oh.
And finally, even once an ion is partially dehydrated and inside, it still has to navigate the winding path. That's restricted intrapore diffusion.
It's not a straight shot through.
Not at all. It's a confined, tortuous path. And the combination of that narrow path plus those interactions we just talked about means the monovalent ions, the ones we want, just find it much easier and faster to get through compared to the divalent ones like magnesium. It's like an obstacle course designed to favor lithium.
Wow. So just to recap, it's the tight physical fit, the energy cost of shedding water, the specific chemical interactions slowing magnesium down, and the tricky path itself.
A multi-pronged attack, absolutely.
These hydrophilic PIMs let the smaller, single-charged ions like lithium zip through with an electric field pushing them.
While effectively slamming the door on the bigger, double-charged ones like magnesium.
It sounds incredibly elegant on a molecular level, but, the proof is in the pudding. What happened when they actually tested these things?
The results are, well, they're genuinely impressive. Transformational, really. They used electrodialysis.
Right, using an electric field to pull the ions through the membranes.
Yeah, coaxing the right ions through the maze. And these AOPIM1 membranes showed fantastic selectivity between monovalent and divalent ions.
Oh, good.
Okay, get this. Potassium over magnesium, K plus Mg2 plus selectivity, was about 11,180.
Whoa.
Sodium over magnesium, Ma plus Mg2 plus, was 300. And lithium over magnesium, Li plus Mg2 plus, was around 230.
230. That's massive compared to what you said earlier.
Massive. And another version, PM SBIOHAO, hit a Li plus Mg2 plus selectivity of about 485.
Incredible. And conventional ones were?
Like Nafion, about 1.8.
1.8 versus potentially over 400. That's a paradigm shift.
It really is. It means you're not just getting some lithium, you're efficiently purifying it. It makes these challenging brines suddenly look very attractive.
And they let the lithium through quickly enough.
Yeah, high permeation rates for lithium around 0.2 to 1.0 moles per square meter per hour. But magnesium transport was tiny, like 10 to the -3 moles per square meter per hour. So fast for lithium, extremely slow for magnesium. High purity, good speed.
Okay, fantastic initial results. But for industry, they need to last, right? And handle real-world conditions like different pH levels.
Absolutely critical points. And they looked good there, too. The AOPI membranes showed really remarkable pH stability.
Meaning?
They kept that high selectivity over a wide pH range from 4 to 10, which is perfect because real salt lake brines are usually alkaline, pH 7 to 11.
So they don't degrade or lose function in those conditions.
Exactly. Selectivity might dip a tiny bit at very high pH, but it stays way above 100. Even at low pH, where permeation slows down a bit, the selectivity remains high. Right. Very robust.
And long-term, did they run them for a while?
They did. They ran tests for 20 days straight. That's about 480 hours.
Yeah.
Stable operation. The Li plus Mg2 plus selectivity did decrease a bit over time from maybe 250 down to about 150.
Still vastly better than 1.8.
Oh, absolutely. Still significantly higher than traditional membranes. And crucially, the membrane structure itself held up perfectly. That's a very encouraging sign for long-term industrial use.
And you mentioned they tested variations to confirm why it works so well.
They did, yeah. It wasn't just luck. They tried things like deprotonating the amidoxime groups, basically changing their charge.
What happened?
Membrane swelled up, selectivity plummeted. Lemang dropped below 10, showed how vital that specific chemical setup is.
Okay.
Then they tried replacing the water-loving groups with water-repelling ones, a hydrophobic version.
Gnat.
Killed the permeation rates. The ions just couldn't move through easily if the channels weren't properly wet.
So those control experiments really nailed down that the specific design, the PM structure plus those hydrophilic amidoxime groups was the key.
Precisely.
Nice.
It validates the whole approach. It's intelligent design, not just a random discovery.
Okay, so great lab results, stable. The science seems solid, but can it scale? You mentioned that solution processability.
Right, that's where they went next. They didn't just stop at small lab samples. They built upscaled electrodialysis stacks.
AJAR units.
Much bigger. An effective membrane area of 189 square centimeters in the stack. They actually integrated these AOPM1 membranes into a working prototype.
Okay, this is the real test then, moving towards industrial application.
Exactly. Proving it works outside the beaker on a more meaningful scale.
And did it?
It did. The results from the scaled-up tests were just as promising. Even in the larger stacks, the membranes kept doing their job, preferentially moving potassium, sodium, and lithium while blocking magnesium.
Still getting that high selectivity.
Consistently over 100 for Li plus Mg2 plus in the stack setup, and they found ways to make it even more efficient.
How so?
By using 2 pairs of the membranes in the stack configuration, they nearly doubled the processing efficiency.
Doubled it. Wow!
And maybe even more importantly, that almost halved the energy needed. Specific energy consumption dropped from around 20 kilowatt hours per kilogram of lithium down to about 11.
That's a huge saving in energy costs and environmental impact.
A massive win. And the process worked well enough to concentrate the lithium up to over 3 moles per liter.
Which is concentrated enough to
precipitate out high-purity, battery-grade lithium carbonate. They achieve purity up to 99.6%.
exactly what battery makers need.
Spot on. And they also tested it with simulated salt lake brines, much messier than lab solutions, and it still performed well, drastically reducing that problematic magnesium to lithium ratio.
Making those real-world brines actually usable.
Turning a challenge into a viable resource.
And that solution processability we keep mentioning.
Yeah.
Being able to make these using existing roll-to-roll methods.
Yeah.
That really seals the deal for practical use, doesn't it?
It's absolutely crucial. It means you don't need bespoke, incredibly expensive new factories. You can leverage existing industrial infrastructure. That drastically cuts down the time and cost to get this tech into the field. It's not science fiction. It's a ready-to-scale solution.
So what does this all mean for you listening and for the future of green technology?
Well, it means these microporous PM membranes, with their super smart design, those hydrophilic sub-nanometer pores, they offer a genuinely sustainable, really efficient way to get lithium from brines.
A potential game changer.
Could be. For supply chain stability, for accessing lithium in more places, reducing environmental impact, and it's bigger than just lithium.
How so?
The design principles here, that clever combination of size filtering, managing dehydration, using specific chemical interactions, these ideas can be applied elsewhere.
Like what?
Think next-generation membranes for advanced water purification, maybe desalination, or recovering other valuable metals from industrial waste, recycling processes too. It all feeds into building a more circular economy globally.
Absolutely. This deep dive really shows that future, the one we read about in papers, it feels a lot closer now. Imagine being able to pull critical resources out of almost any salty water source, lakes, geothermal discharge, industrial effluent, massively cutting our footprint for devices, EVs, grid storage, everything.
It opens up so many
It
possibilities.
really makes you wonder, doesn't it? What else could we sieve out of our waste streams, out of unconventional sources, if we keep applying this kind of incredibly clever molecular engineering? What other crucial resources do you think these membranes might unlock next?